Welcome to another episode of learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of those problems that have appeared in the CSIR National Eligibility Test held on February 28, 2025. Today, we discuss the solution of a problem from the section Linear Algebra, which is related to the concept of commutator of two matrices. Now, this question is placed in part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. This question has the ID 704153. Yes, this question is suitable with some modifications for all these examinations. Right, the given question is, let A, B be 2 by 2 matrices with real entries and M is equal to AB minus BA. Let I2 denote the 2 by 2 identity matrix. Which of the following statements are necessarily true? We are given four options. Option 1. If A and B are upper triangular, then this M is equal to AB minus BA is diagonalizable over R. Option 2. If A and B are diagonalizable over R, then M is diagonalizable over R. Option 3. If A and B are diagonalizable over R, then there exists a lambda belongs to R such that M is equal to lambda times the identity. Option 4. There exists a lambda belongs to R such that M square is equal to lambda times the identity. Let's now discuss the solution of the problem in detail. We have 2 by 2 real matrices capital A and B, that is AB belongs to M2 over R, and given M is equal to AB minus BA. What is AB minus BA? It is the commutator of the matrices A and B. First we claim the trace of a commutator is always 0. Trace of M is equal to trace of AB minus BA, that is equal to trace of AB minus trace of BA, that is equal to 0. Why? Because any two matrices A and B of the same order, then the trace of AB is equal to trace of BA. So, for any two square matrices AB of same order, the trace of the product AB is equal to the trace of the product BA. That is why this becomes 0. Hence the result, the trace of any commutator is 0. Now, the characteristic equation of M is given by lambda square minus trace of M into lambda plus determinant of M is equal to 0. Now, trace of M is 0. This becomes lambda square plus determinant of M is equal to 0. Now, apply the Cayley-Hamilton theorem now. The Cayley-Hamilton theorem states that every square matrix satisfies its characteristic equation. Therefore, M square plus determinant of M into I2 is equal to 0. That will imply M square is equal to minus determinant of M into I2. So, now determinant of M is, this implies M square is equal to lambda times I2, where lambda is minus determinant of M, which is a real number. Thus, there exists a lambda belongs to R such that M square is equal to lambda times I2. So, thus we have established the truth of the option 4. So, option 4 is true. We continue the discussion of the remaining options in the next slide. we call on option 1. If A and B are upper triangular matrices, then M, their commutator, is diagonalizable over R. Now, let A is equal to AB 0C, B is equal to PQ 0R. Both of them are upper triangular matrices. Both of them are upper triangular matrices. First, we prove that the product of any two upper triangular matrices is again an upper triangular matrix. Then M is equal to we now prove the commutator of any two upper triangular matrices is again a upper triangular matrix. That's the correct statement. So M is equal to AB minus BA. Write down A, write down B, minus, write down B, write down A. Multiply. So after multiplication, you get this matrix minus this matrix, and subtract, you will get this matrix, and that is equal to 0 Q times A minus C plus B times R minus P, second row 0 0. So what is this? This is again a upper triangular matrix. Thus we have proved if A and B are upper triangular, then their commutator is also upper triangular. So take any two upper triangular matrices, then their commutator AB minus BA is also an upper triangular matrix. Right. Now we let A is equal to, specialize the matrices, A is equal to A0 0C, that means B is 0. You have put B is equal to PQ 0R with the condition A not equal to C, Q not equal to 0. Now calculate the commutator. So then M is equal to AB minus BA is, now you can use the above result with these conditions, then that will be equal to 0 Q times A minus C by 0 0. Right. And what is, now this is of the form 0 alpha 0 0, where alpha is Q times A minus C. Now you have put the conditions A not equal to C, therefore A minus C not equal to 0, Q not equal to 0, so their product is not 0, therefore alpha not equal to 0. And the other part will become 0 because B is taken to be 0. Right. So thus we got M is equal to 0 alpha 0 0, where alpha is not 0. Now take this matrix M and square it, you will find it is a 0 matrix. That means to say M, that is 0 alpha 0 0, is a non-zero nilpotent matrix of index 2. Why it is non-zero? Because there is one surviving element alpha. Right. Now M is not diagonalizable. Why M is not diagonalizable? We have the famous result that every non-zero nilpotent matrix is not diagonalizable. So there's what we have proved is the commutator of two by two upper triangular matrices of the form given in 1 here like this is not diagonalizable. Therefore, option 1 is not true. Right? But some of our students ask, sir, why don't you give a counter example instead of proving this theoretically? Yes, we give a counter example. But now I will add one comment here. How counter examples are created? Counter examples are created, an argument like this. From that, you specialize two matrices. We have already specialized, but too much of specialization also you can make. The specialization also you can make. So this is a counter example. So in this, put A is capital A, small a is 1, c is 0. In B, we put p is equal to q is equal to 1, r is 0. Now a not equal to c, q not equal to 0. Right, a not equal to c, 1 not equal to 0, q not equal to 0. Both are upper triangle, obviously. And their commutator m is equal to ab minus ba, compute, you will get 0, 1, 0, 0. It's again, that means in this counter example, you are getting alpha is equal to 1. Thus, continue our argument, m square is the 0 matrix. That means m is a non-zero nilpotent matrix of index 2. Therefore, m is diagonalizable because every non-zero nilpotent matrix is not diagonalizable. Hence, option 1 is not true. Now, here itself, it gives a clue for the next option also. In the next option, if A and B are diagonalizable, then M is diagonalizable over R. Is it so? Now take these two matrices only. They are upper triangular matrices and each is diagonalizable because A has eigenvalues 1, 0, distinct eigenvalues. B also has distinct eigenvalues. So therefore, both are diagonalizable. And their commutator is this one. And by this same argument, M is not diagonalizable. So thus establishing the next option. So we go to next option, option 2. If A and B are diagonalizable over R, then M is diagonalizable over R. We take this counter example. A is equal to 1, 0, 0, 0. B is equal to 1, 1, 0, 0. This is the same counter example what we have already considered. A and B are diagonalizable. Why? Because both are upper triangular matrices. The eigenvalues are 1, 1 and 0. They are distinct. So A and B are diagonalizable over R because they have distinct eigenvalues. Now M is equal to the commutator AB minus BA. So I have just multiplied and you will get 0, 1, 0, 0. This is the same answer what you got in the last slide also. Right. Now note that M square is the 0, 2 by 2 0 matrix. Thus M is a non-zero nilpotent matrix of index 2. It's non-zero because there is an element 1 which is surviving in the matrix. Right. M is not diagonalizable because every non-zero nilpotent matrix is not diagonalizable. Thus, the commutator of two 2 by 2 diagonalizable matrices is not necessarily diagonalizable. Thus, the option 2 is not true. We call on option 3. If A and B are diagonalizable over R, then there exists a lambda belongs to R such that M is equal to lambda times I2. Say, take the same matrices A and B as given in option 2. A and B you take and calculate its commutator. Then you got 0, 1, 0, 0. So, is M is equal to lambda times I2? It is not equal to lambda times I2 for any lambda. Therefore, this option is also not true. Taking the above diagonalizable matrices A and B, we see that the commutator of A and B, M is equal to AB minus BA is 0, 1, 0, 0, which is not equal to lambda times I2 for any lambda belongs to R. Therefore, this option, option 3, is also not true. Summarizing all the options, we get the answer to this question is option 4. That is the detailed discussion of the solution of this problem. I add my own comment here that this is all right. It's looking a very good question. But in the examination, getting such a kind of arguments and counter examples looks very difficult. Anyway, I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. I am sure we will be meeting again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.